So I'm pleased to introduce Daniel Stilck França, who is at the University of Copenhagen. Before the University of Copenhagen, he was a PI in Lyon. He, before that, did a postdoc, so going backwards in time, at Copenhagen, did his PhD in Munich, and pleased to have him today to talk about provably efficient learning phases of matter by dissipative evolutions. And I think the thing that I've always liked about Daniel's work is that it nicely sort of blends different worlds. So it's really theoretically rigorous, sort of drawing on quantum algorithms and quantum information theory background, but he applies it in applications that are sort of interesting to a bigger community of physicists. So yeah, I'm excited to hear this today.
Thanks a lot, Zoe, for the very nice introduction and also for the invitation to be here. It's also so nice to see so many faces.
So many that I don't have anywhere to say.
Yeah. So thanks a lot for this, for the interest in this. So yeah, as Zoe mentioned, this is going to be a talk on learning phases of matter, and you can find the relevant technical results. I mean, the name of the paper is the same as the talk, and here's the archive link. And this is joint work with these three fine gentlemen, so Emilio, Cambyse, and James at TU Munich, INRIA in Saclay, Paris, and University of Maryland, respectively. All right, so let us start by just say that this is sort of like a work at the intersection of machine learning and quantum physics, and there are lots of things happening at this intersection, and many different people understand different things when they talk about machine learning and quantum physics. So you could, for instance, and I know that there are these different facets of these two topics are well represented also here, so you can look at, for instance, quantum algorithms to solve machine learning problems, or you could maybe try to look at classical machine learning algorithms to simulate quantum systems, two things that are done over here. Or what we'll be doing in this talk is sort of how to then sort of train a classical model on quantum data. Okay, so you'll be given access to some experimental data, and you want to train some model on this data. So this is sort of the setting we'll be interested in today. I'll be a bit more precise in a few minutes, but essentially it will be this problem of so-called learning local properties of phase of matter. Again, I'll explain this in more detail in a second. And we'll be focusing on getting some rigorous sample complexity bounds in the sense of like how many experiments do I have to perform to solve this problem, and I really want to get some provable bounds on this. Okay. So the main motivation for this paper is a paper by Robert Huang and other folks from back then Presco's group at Caltech. It's called Provably Efficient Machine Learning for Quantum Many-Body Systems. So that paper is really our departing point. And what did they do? So they looked at the following problem. Okay, so you're given some family of quantum Hamiltonians which are indexed by some parameter x. Okay, so these are our hx, and you have this very important and nice promise that for whatever x you pick, this Hamiltonian will be gapped. Okay, so there is a constant that bounds the difference between the ground state energy and the first excited state. So there's a constant there. Okay, energy gap. And Hamiltonians that have this property are very special. They have many different properties, okay? But we are given some sort of parametrized family of them, which is supposed to model some gapped phase of matter, okay? And, well, we then are given some very special machine, this cartoon over here, such that if we press this red button, we will get some randomly generated label X, which will label some Hamiltonian. and the corresponding ground state. So if I press X, I get this classical label, so someone hands you a piece of paper with what X is, and on some quantum device, you also get psi of X. All right? And what is our goal here? So we have access to this very special machine, but in general, preparing these ground states, even if you have a nice gapped Hamiltonian, can still be a very difficult task. So even though we have this very special machine, we should think that using this machine is very expensive. So what we want to be able to do is to use this machine a few times and then collect some data, and then from this data train some sort of model that will allow us to say something about the physical properties of states we haven't seen yet. Okay, so I want to press this button a few times, collect some samples, and then if someone else comes along and asks me, what about this and that property of the ground state for some parameter I haven't seen yet. Okay, and then instead of going to this machine, and by the way, we have no control over which X we'll get, it's just given it to us at random. Instead of using this machine again, we can just go to this model we trained and then estimate some expectation value on this ground state we have never seen before. Okay, so this is sort of the setup. And it's sort of a setup that mixes a bit of machine learning, right? Because this sort of thing where you press a button and you get a label and you want to train a model is very machine learning-like, right? But also has some many-body physics aspect to it because we want to infer properties of some ground states of gapped Hamiltonians. So this is the setup of this paper by Wang and others. And we're going to build upon that. So, any questions so far on this setup?
Can I have one question? So once you get the state, you cannot measure many times to determine the state.
Very, very good point. Yes. So once you press the button, you get X and psi of X. You measure it once, and it's gone. And every time you press the button, you get another random X. All right. What was their main result? So their main result is that you can achieve some small error for predicting all local observables over the whole phase, not all local observables, but a given local observable over the whole phase, if you're happy making errors on average only. And the training data they need is a polynomial in the number of observables you wish to estimate, so the number of O's, right? But it's very costly in the precision. So in formulas, what they can do is essentially the following thing. So they can train some model that, with the promise that this function f of O satisfies that if I look at the square of the error I make on average over all the ground states, it's going to be smaller than some epsilon. Okay, so in some sense, on average, this function you're going to learn is going to perform reasonably well, which is quite interesting. But there are some things we don't like about this result, namely the fact that you have this 1 over epsilon scaling over here. So even if you are in the even moderate precision regime and you only want to get a few observables, this is going to be huge, right? So this is something we don't like, but it was the first result in this direction. So of course it's not necessarily optimal as well, and it's already quite non-trivial. But how do they do this? So they use this so-called classical shadows framework to get some training data. I'm going to explain what that is later on. If you don't know this, don't worry. They then train a so-called kernel representation for these observables, and then the math involved is kind of complicated, and it's a long proof. They use so-called quasi-adiabatic continuation theorems, which essentially tell you that as you vary the value of the parameter of these Hamiltonians, the ground state doesn't change in a completely crazy way. Okay, and so sort of the landscape for these functions you're trying to estimate isn't completely crazy because of these theorems, and then you're able to say something rigorously. Okay, so that's their result. So two questions that immediately come up are, can we generalize and improve these results? And by generalize, I mean going beyond this setting where we are just looking at gapped Hamiltonians. Can we also consider other families of physical systems? Can we consider, say, mixed states? Like, under what conditions can we derive similar results? And when I say improve, I mean mostly the number of times I need to press that button, right? Because sort of having this 1 over epsilon in the exponent is not very satisfactory, right? You'd expect to have fewer samples in the setting where you don't require too much precision. And another thing I asked myself when I saw this paper was, how much machine learning machinery do we actually need to get these results? Like, how much of the heavy lifting is being done by the machine learning hammers they use, and what part is just, let's say, something else, let's say some property of quantum systems instead. So that was another motivation of mine getting into these problems, to sort of understand what the machine learning part of it is doing for us. Okay, so before I move on to our setting, are there further questions on this setting we're trying to build upon and generalize? Yes?
Why is the gapped requirements important to the proof, and is there any other requirements?
Right, why is the gapped? So essentially, because, okay, I don't want to get too deep into this, but essentially if you look at two Hamiltonians, two ground states of Hamiltonians that are gapped, and you can find some sort of gapped path between them, which we do because we have this parametrized family of states, then you have a very nice way of going from one ground state to the other through adiabatic evolution. So the gapped tells you that this adiabatic evolution will also be sort of fast. I mean, adiabatic fast is a bit, but I mean in the sense that the time it takes from one to the other isn't too long. And this is super essential to using at least their methods, show that the landscape for these functions you're trying to estimate isn't too crazy. So that's why you need this gapness. Yes?
So, philosophical question. So when you say learn phases, it means it doesn't mean distinguish phases, because having a quantum phase transition between two different quantum phases would imply the exact opposite would require, and the exact opposite, that your gap must go to zero in between, right?
Right. Precisely, yeah. So that's actually maybe something I should have already mentioned before, which is that they also consider this other very interesting problem of distinguishing phases. So let's say I give you the promise that either, like, I give you a value of x, and I promise you that it's either in phase A or phase B, and it's the job of your machine learning thing to decide which is which. So that's also something they consider. You can do similar things for this problem, but here I'm focusing more on, like, given you are always in the same phase, you want to, like, estimate everything in that phase. Yeah. Other questions? No. Okay. Okay. So I'm gonna now change what I mean by a phase. And I don't know, there are like many different definitions of a phase. And I personally like this one because it works well for our purposes, which comes from a work by Perez Garcia and Koser, where they define the so-called dissipative phases. Okay, and why do I like it? Well, first of all, it's a definition of phase, of matter, that allows you to also talk about mixed states. So if you want to, let's say, talk about thermal states and things like that, then this sort of adiabatic evolution or shallow circuit definition of phase that other people use doesn't really work that well. And another thing is that, for instance, many definitions of phases don't really make a lot of sense if you're looking at finite systems. So this is another feature that I like about this definition of phase, is that it also works for finite systems. And what is this definition of phase that Perez Garcia and Koser put forward? It works as follows. So I say that two states, rho 1 and rho 2, are in the same phase if there is some time-independent, local, and short-time dissipative process that will take me from rho 1 to rho 2 and vice versa. Okay, so if I can engineer some sort of dissipation, and I mean, when I say dissipation, I mean also you can also have some coherent terms on top, but that is time-independent, that allows us to move back and forth between rho 1 and rho 2 and doesn't need a lot of time, then we say that they're in the same phase, and we also allow for some auxiliary systems. And then as you want to like consider systems of different sizes, there are also some compatibility conditions you need to take into account, but I'll just put that under the carpet. Ask me later if you want to know what these compatibility conditions are. But essentially the idea is, again, just if you can move between states through local dissipative processes, you say they are in the same phase. Okay. Now, why do I like it? I already gave you a few reasons. There are more. So first of all, it includes this usual adiabatic or shallow circuit definition of a phase. So for instance, many people consider this. So what is this adiabatic definition of a phase? You say that two states are in the same phase if you can move from one of them to the other with some Hamiltonian whose gap doesn't close, right? So this is sort of one possible definition. Or if you can, which is equivalent, go from one to the other by applying a circuit of constant depth. So these are two possible definitions of phase. And it turns out that if you're happy with these definitions, then this definition of Perez Garcia and Koser can also do that. So states that are in the same phase with respect to these definitions are also in the same phase with respect to this one. So it's more general. Okay? And in particular, this definition of phase also includes the setup of this long paper I mentioned previously, because they were considering gapped phases, right? So, okay, that's nice. So it is indeed a generalization of what we were considering before, but it has more structure somehow. Because, and why is the intuition why this is a nice definition of phase? Well, first, you'd expect that if you can only act locally on the system and only for short times, then this is not enough to create long-range correlations, right? Which is what you would expect if you're always moving in the same phase, right? And that the local physics of different states in the same phase should also be similar, right? And again, it works for mixed states, which is something I also like. And now, working with this requires us to work with time-independent dissipative processes, which I personally like more than time-dependent Hamiltonians. And just again, some intuition. It is important that we consider that we only allow for moving between that it's important that we are able to move in both directions, right? Because, for instance, it is easy to, let's say, go from an ordered phase to a disordered phase with some local dissipative process. It's very easy to destroy things, but it's not easy to go back, right? So sometimes it might be the case that you can go from one to the other through some local dissipative process, but not the other way around. So please recall all the time that we are able to go both ways. All right. I think this is all I wanted to say for now about this sort of high-level idea of this dissipative phase definition. And now we're going to dig in a bit more formally into what I mean by these two points. Okay, but yes. So, how do we formalize this idea that if you have a local time evolution that for short times, that the local physics should be similar? One way of formalizing this idea is through so-called Lieb-Robinson bounds. What are Lieb-Robinson bounds? So Lieb-Robinson bounds tell us that if you have, let's say, an observable on a system here that is supported over here, and you evolve it for some short time, then this will be mapped in the Heisenberg picture. This will be mapped to an observable that will be on a potentially larger system, but not everywhere if you allow for a small error. So it tells us that local time evolutions have some sort of effective light cone. So if you're willing to make a small error, local things are mapped to local things. So local time evolutions for small times cannot change things globally. That's the moral of the message of the Lieb-Robinson bounds. And one way of formalizing this is to say that if I look at the time evolution of the observable under our local dissipative process, or any sort of local time evolution, and I compare it to the time evolution I obtain when I just look at the terms acting on a ball around this point. So essentially, instead of looking at the time evolution around the whole thing, okay, I truncate to terms that are sort of acting on a ball. I mean, okay, this is definitely not a circle, but hopefully you get the idea. If I truncate to all the terms only acting at the distance r from this region, then I will get a very good approximation of the global thing. And how good this approximation is depends on the evolution time. The longer I evolve, the more things spread out, of course. But the larger I make this region, the better the approximation as well. So usually you have this sort of bound that says that the more I enlarge the region, the better the approximation becomes, and the more I evolve, the larger the region I have to make it. There's this sort of effect. Okay, and this function, both of these functions are usually exponential. So you get a better you get exponentially better as you increase the radius, and exponentially worse as you increase the time. Okay. All right. Questions? No. Then let's continue. Okay. So now, what is this? I said before that I want you to be able to go from one state to the other in small times. What does this mean formally in this definition of phase? Well, it means the following thing, that for every state, let's say rho 1 and rho 2 are two states in this phase, all right? And I want to be able to say the following. I can apply this sort of dissipative process on the state rho 1, and then you can ask me how long will it take for the marginals on some region of size A to be close, okay? And I'm imposing what is called local rapid mixing, which essentially says that I'll converge exponentially fast for each region up to this correction term, which scales with the size of the region I'm interested in. Okay, so roughly, I mean, this means that as I impose that this convergence rate is independent of the size of A, if I evolve the state for a time which is logarithmic in a region, I'll approximate the marginal quite well. So I can move from one state to the other in a time that scales logarithmically with the size of the region, for each region I care about. Okay, so this is what I mean when I say that I can easily go from one state to the other through a dissipative process. All right, and note that this is very fast, right? So it's logarithmic in the size of the region, and again, these guys are very local. So this means that we are converging faster than local long-range correlations can form. So as we are converging so fast, there's not enough time for different qubits, let's say qubits that are very far from each other, to actually talk to each other before they've actually converged. So because of this local rapid mixing, I cannot create long-range correlations in row 1 that are not present already in row 2 by acting with this local dissipative process. Okay. All right. Okay, so hopefully I explained a bit this dissipative phase framework of Perez-Garcia and Koser, and now I'm going to explain how we use it in our result about learning the phases. But before that, maybe I already lost you on the Huang definition, so I'll just quickly go back to that so that we can make some sort of analogy. Again, what was the setup? Press this button, get ground state of some gapped Hamiltonian, where again this is supposed to represent some sort of states coming from some phase of matter, and we want to be able to predict local observables of all the states in the same phase of matter. Okay, this is where what we want to sort of mimic. And how are you going to mimic that? Well, instead of going for ground states in this gapped phase, we're just going to say that we have states rho x, so some family of states, some parametrized family of states, which are in the same dissipative phase. Okay, so we're going to use this dissipative definition instead of the ground state definition. Essentially, this parameter corresponds to the Limbladian, or like the dissipative evolution we get from evolving from a fixed reference state rho star. So what do I mean by that? So imagine, so we know that we have this phase over here with a bunch of states, right? And we know that if I pick any two states, rho 1 and rho 2, there is this local Limbladian that will drive me from rho 1 to rho 2. So I can like move between them, right? But we want to get some sort of parameterization over all of them. And because we, what we could do then is just look and define any state here, let's call it rho star. And we also know that we can go from rho 2 to rho star, rho 1, rho star, and vice versa. And the way we'll parameterize the states is just in terms of the evolution that will drive us from rho star to any row in the set over here. Okay? And we can pick any state, right? You just pick your favorite reference state in this phase, and then you can sort of parameterize all of them in terms of the local evolution that will drive you from rho star to rho 1 or rho 2. All right? And what is the thing that we also want for these dissipative evolutions is that these states rho x, they are the unique fixed point of this dissipative process. All right? Which means that if I just turn on this dissipative process, feed it any initial state and run it long enough, it's going to spit out rho of x. Okay, and this will be important to us, and is also part of this dissipative framework. But what is important? I mean, I'm saying that if you evolve it for very long, you're going to get the right thing, right? It's this limit with t going to infinity, but you're only given the promise that it's going to be fast if I move from one state to the other in the same phase. So if I start from a state in a different phase, I don't have the promise that this is going to converge fast, right? Okay, so just this side remark. All right, so this is our setup.
Can I ask a question?
Of course.
Just a really basic one. Your definition of these dissipative phases is rapid mixing condition. You've got to have that. So this Lindbladian, it's got to be dissipative. You can't have like just local unitaries, short-time unitaries.
No, because I mean, so.
Yes, I initially thought it was any process. I initially thought the dissipative stuff just made it more flexible.
Yes.
But no, it's actually a restriction. It's got to be sufficiently dissipative in order to be in the same phase.
Yeah, but so in the Perez Garcia and Kozer paper, what they do is, I only briefly said that, it includes this sort of adiabatic or shallow circuit definition as, so you can sort of massage it into this one. And how do they show it? They show it that if you have, let's say, an adiabatic evolution or a shallow circuit that maps rho 1 to rho 2, they give you a recipe of how to transform that into such a dissipative process. So if you give me, let's say, a shallow circuit that goes from rho 1 to rho 2, then I can write down a dissipative process that will do the same thing.
So okay, but there'll be a dissipative process, but
A
there
different-
could also be a unitary process.
Yeah. So
Process.
So if you give me this unitary process, I can cook a dissipative process for you.
So the purity can stay the same.
Yes.
So maybe something simple that I didn't get, but if your Lindbladian has no particular symmetries, then it should rapid or non-rapid mixing, the steady state should be unique, and therefore it should convert. It should go to a steady state no matter what the starting point is.
Yes.
Now, here instead you are saying that depending on the time it takes to get there, you are going to say if it is the same phase or not. But does it necessarily mean? I have the impression that this is impossible unless you assume that your Lindbladian has some symmetry, and so some different. So otherwise, the steady state is always unique, and it is always reached with a time scale which is the inverse Liouvillean gap.
Yes. So, but this inverse Liouvillean gap could be very small, right? So,
Sure.
so for us to have this sort of behavior, one necessary thing is that so if you want to have this sort of behavior, this rapid mixing for all states, then the Liouvillean gap has to be
Finite.
Yeah. And then you're sort of in a trivial phase.
Yeah, but what you wrote in the next page, when you annotated, the few pages later, you annotated that that's what I'm missing. Yeah, that's exactly the point.
Yeah.
You're saying that, okay, so L, the Lindbladian is also depending on X, so it will be a different one for different, because otherwise, okay. I see. So actually, these different Lindbladian may have different mixing times, so different Liouvillean gaps.
Yes, but what is super important here is that, again, if, as you were observing, right, if this behavior is the typical behavior, but I only expect this to happen fast if we are in the same phase. So if it could be that for some initial states you have, then this is going to take super long.
Okay, but I think this is also associated to symmetries, because different phases must be associated to symmetries and to broken symmetries in particular. So there must be something. Otherwise, if it's rapid, it's always rapid. So if you're assuming that for some x, this thing is going to be not rapid, then it means that somewhere there has to be something that is changing in the
Completely agree with you. So the way you could maybe think of it is, let's say you have some symmetry, as you were saying. So you have like you can, let's say, decompose this lymphladin into different blocks.
Okay.
And then if you're in the same
in
symmetry,
the same block, you go faster.
Yeah,
If
yeah.
you are in different, yeah, okay.
Yeah.
That's clear. Thank you.
Okay. Other questions? All right. So hopefully, if we are now a bit more familiar with this concept of dissipative phase. Recall, so how is it different than the Huang paper? Well, it's not that different. The only thing is that now, instead of assuming that I get the ground states, I press the button and I get states from the same dissipative phase. And our goal will be exactly the same. I want to be then able to, given some labels I haven't seen before, be able to predict local properties of the associated states. Okay, before in this original Huang result, they assumed that the distribution over parameters was uniform. We don't want to necessarily make this assumption, and later I'm going to make a lot of comments on this point because you'll see later why. But yeah, so before I explain how we get our result, I'll tell you what our result is. So our result tells us that the number of copies you need, so the number of times you need to press this button, if you want to solve this problem, and by solve this problem, I mean find the function f that depends on this observable such that for each label, right, the error you make on predicting this expectation value is at most epsilon, scales like this ugly thing. So why is this nice? Well, first, it's if you recall, I mean, I should have had it here as well, just for you to be able to compare it. But the Huang result scaled like this, and I think I was not even consistent with the capitalization of m. Apologies for that. So if you have m observables and accuracy epsilon, the result scaled more or less like this. So we see that now the m is inside a log, and the accuracy is still not polynomial, but e to some polylog, which is exponentially better, right? Another thing I would like to emphasize is the fact that we have a supremum over all parameters here. Recall that for their result, they only had an expectation. So we can say that for whatever x you give me, I'm going to get a good estimate. And I should say that at the same time you were working on this, there was a follow-up work by Laura Lewis and essentially the same people who did the first work, who achieved a similar scaling as ours. But for this setting of ground states, not this generalized setting I'm talking about. And their approach does not need a nice distribution for the parameters. However, they don't get this supremum error. They only get that the error is small on average. Okay, and our estimator is very simple. We don't need any fancy machine learning results. And it seems to me at this stage that sort of the machine learning results these other people are using are only important to be agnostic about the distribution of samples of labels you're getting from. So I will need to assume that the distribution of samples I'm getting is nice enough. They don't need this. They can just say like, hey, whatever, yeah.
I mean, surely the extreme will just get one data. If you have a delta function distribution, it's got to break down at some point.
Yeah, well, not really, because the point is that we are also measuring errors in different ways, right? So.
So it's all in distribution variables.
Yeah,
yeah. You need to actually estimate that point. Okay.
Yeah. So the point is that they are doing it in this metric. We're doing it in the supremum. So they'll only see that point, and they'll be able to. So that's why I see like. So they're using lasso to train the thing, and then they can get guarantees of this form, and they don't need, and we need to assume something about the labels. Yeah. All right. All right, so how do we get there? Well, we use so-called robust shadow tomography. So I assume not everyone here is familiar with shadow tomography, so let me maybe quickly explain that before I explain the robust one. So how does shadow tomography work? It's a very popular thing nowadays, has been popular for a few years, I guess. And it's sort of a procedure to, for a lot of properties of your quantum states from not a lot of samples or not a lot of experiments, okay? And how it works, and it's quite experimentally friendly, so people can actually do this in practice and have done so. So what you do is you get your quantum state, and then you measure each qubit in a random Pauli basis. Okay, so you pick your favorite, you draw one Pauli basis at random, you measure in that basis, and you record what the result was. So for every time you do this, you'll get some sort of Pauli string out, okay, which just records what was the outcome, whether it was 0 or 1, and in which basis you measured it. Okay, so you just label it in terms of the eigenstates of the different Paulis you've measured, right? And then you repeat this procedure many times, okay? And for each time you do this procedure, you obtain what is called a shadow, okay? And a shadow is just some sort of affine transformation on this sample you got. So you just take this string or this product state, you multiply it by 3, and then subtract the identity. Note that this is not a quantum state, because this will in general not be positive semi-definite because of this minus identity. But it turns out that if you look at sort of the empirical average of these things you've measured, and you look at marginals of small enough size, they will converge very fast. So if you're only interested in capturing local information about your state, this shadow tomography protocol is very efficient, because the number of samples you need actually only scales for a fixed precision, only scales exponentially on the sizes of the subsystems you wish to recover. So if you want to get, I don't know, like all 4 body marginals, the number of experiments you're going to need to do for fixed precision is going to only scale exponentially in 4, not in the total number of qubits. So that's why it's quite a popular method. And here we used a variation of this method, which we developed, which we call the robust shadow tomography. And the idea is that, well, instead of assuming you always have the same state, so the original shadow tomography is you get the same state measured again, what we just look is, what we consider is a small variation of that problem. Namely, you're not given the same state, you're just given the promise that for each copy you get, the states are somehow close locally. So you don't need the states to be exactly the same, you can tolerate some small local differences, okay? So it's not an IID thing, you just have small local differences. And what we show is that even in this more generalized setting, you get a very similar scaling for the complexity, but with a worst exponent. So if for shadow tomography, let's say if you want to recover all marginals of size R, you need something like 3 to the R samples. In our case, where they're not exactly the same, we instead prove it with 12R. Maybe you can bring this exponent down, but the point is just that you essentially get the same result if you don't care about the exponent, only the scaling. If you don't assume you always get the same state, you just get states that are close enough locally, all right? So why do we care about this robust shadow tomography result in our previous setting? Well, we were saying before that, well, we have these Lieb-Robinson bounds, we have this rapid mixing, and it tells us that the local physics of different states should be similar if they're close enough as well in this phase, right? And robust shadows tells us that if we want to look at local properties of a state, it's not really necessary to get exactly the same state. We just need to get a bunch of states that are not too far of it locally, and the estimator will work equally well, okay, and with similar scalings. So if we put together these two ideas, what is sort of a natural approach to our problem? We sort of try to show that as long as we get enough points so that we can make sure that we cover the corner of the space, of this face, then using these shadows, we'll be able to recover all the points in that corner, right? That's more or less the idea. Let's make this a bit more formal. So now for simplicity, let's suppose we have an observable O that is on the first side, and we have a chain of qubits. It's a 1D system, so we have our O1 over here. And we're going to assume that the parameters for two states in this phase, rho x1 and rho x2, are the same. So they are exactly the same up to side k. Okay, so all the parameters of the state are the same. Now we then, considering that they look very similar up to side k, at least in the parameterization, we would maybe expect that their expectation value on O1 is also close. How do we show this using the definitions we had before? Well, we're going to do it as follows. So imagine now we are looking at trace O of 1, x1 minus rho x2. And we now have to use we want to show that this thing is small. We want to show that if they agree on k sides, then they're going to be similar. How do we get that? Well, we know that this guy, if we apply Lx1